Hello, everyone. Based on what you wrote on discussion groups, I tried to write down some illustrations about eigenvalues and eigenvectors, and I hope it helps. So why do we start with A, which is the matrix, times nu, which is the vector, equals lambda, which is going to be eigenvalue, or is a number in this case, times nu, which is the vector. So normally when a matrix changes both the length and the direction of the vector. But sometimes an eigenvector happens. This is a special vector whose direction does not change when multiplied by the matrix. So between all those things that may happen by multiplying a matrix to a vector, some of them are called eigenvectors, that they are special vectors that their direction does not change when multiplied by a matrix. The matrix may stretch it, shrink it, or even reverse its direction, but the resulting vector remains on the same line. It means that if this is the vector, anything that happens when a matrix A applies, and if the answer is whatever vector, but it can have any length, but the direction is on the same line. It can be same direction or can be the reverse, but the same line, not something like this. So this is called eigenvector. And so if the output vector points in the same direction as V, then it must be some multiple of V. That multiple is called eigenvalue. So if the red ones are the eigenvectors, there is a relation between the length of the blue one, the original one, and the length of the new ones. That relation is a number called eigenvalue. For example, if eigenvalue is 3, as you see in this equation, that would be the eigenvalue, and it means the vector becomes 3 times longer, but keeps the same direction. So it has the length 3 times the original one, but the same direction. Or if eigenvalue is -2, it means that the length of the new vector is double in time in terms of length comparing the original one. And since we have a negative, the direction is reversed, but it remains on the same comparing the original vector. This is why we use this equation. And now, how can we solve it? In order to solve it, as you have seen in like equations of the numbers, we can subtract lambda nu both sides. So the right side would be 0, but the left side would be a nu minus lambda nu equals 0. And if we factor out nu, that would be a minus lambda times nu equals 0. The amount inside the parentheses cannot be done in terms of mathematics because A is a matrix, lambda is a number. We cannot subtract a number from a matrix. Let's say we cannot write 1, 0, 2, 3 minus just 3. This is not correct. In order to do something that this subtraction be valid in terms of mathematics, we're going to multiply it by one of the word of matrices, which is the matrix of identity, which is, if it is 2 by 2, that would be 1, 0, 0, 1. If it is 3 by 3, that would be 1, 0, 0, 0, 1, 0, 0, 0, 1. These are called identity, and they work as 1 in the world of matrices. So when we do this, this can be done in terms of mathematics. And this is called a homogeneous system, as we have seen in the lectures. Now, the question is, how can we solve this homogeneous system? So as we talked before in the lecture, this homogeneous system has a trivial zero solution, which is not helpful in this case because an eigenvector cannot be a zero vector. So we're going to search for another solution which will be a non-zero solution, and that happens when the coefficient of this equation or the matrix that we have here is singular. You know what singular means? It means that the determinant should be zero. So in order to solve this system of equations, we're going to find the determinant of a minus lambda I equals zero. And we know that this is called characteristic equation. So in order to solve this, we are going to solve determinant of this equals zero. It gives us an equation. We solve that, and we're going to find eigenvalues. These eigenvalues are the numbers that help us in order to find eigenvectors. So after finding each eigenvalue, we substitute it back into the formula that we had, and it helps us to find the corresponding eigenvectors. As we talked before, for each eigenvalue, we're going to have an eigenvector which is related to that. So let's talk about two examples. The first one is how to find eigenvalues and eigenvectors. Let's say we have this one. This is the same question as we had in the review worksheet. So in order to solve that equation that we just talked about, the determinant of a minus lambda I here means the determinant of, let me write it completely, 1 minus 2, 2, and 1 minus lambda times the identity matrix in the size of the matrix that we already have. This is a 2 by 2 matrix, so the size would be 2 by 2 here. It means that this determinant is going to be done for the matrix of 1, negative 2, 2, 1 minus. If we multiply lambda, that would be 0, 0 lambda here. So inside the parentheses says that we're going to have a matrix 1 minus lambda here, negative 2 minus 0 here, 2 minus lambda here, 2 minus 0 here, and 1 minus lambda here. And we're going to set that equal to 0. So we can jump from here to here to see that always, in order to find this equation, we're going to only subtract the diagonal of the given matrix by lambda. So you can skip this part and this part and just start with this equation and then write that as you see here. Now we have this one. How can we find the determinant of a 2 by 2 matrix? That would be the multiplication of these minus the multiplication of others. It gives us 1 minus lambda squared minus 2 times negative 2, which will be negative 2, so positive 4 here equals 0. We can subtract 4 from both sides, so we're going to have negative 4 here. We know that the power 2 of whatever we have cannot be equal to a negative number in real set, but it can be done in complex numbers. So from here, lambda would be 1 minus lambda would be plus or minus 2 times I, because if you don't remember, I can write it as 1 minus lambda equals square root of -4. So 1 minus lambda would be square root of -1 times the square root of 4, which means 1 minus lambda is going to be 2, and square root of this is plus or minus 2. And square root of -1 would be I. And from here, I got this one. And from here, lambda would be 1 plus or minus 2I. These are called eigenvalues. We're going to plug in these numbers. One of them, lambda 1, is 1 plus 2I. The other one, lambda 2, is going to be 1 minus 2I. We're going to plug these numbers here, and for the next one, the same process, in order to find eigenvectors. So let's do these here. Let's say lambda 1 is 1 plus 2I. The matrix that we had, let me write it here again, was 1 minus, so that matrix that we had was 1 minus lambda, -2, 2, and 1 minus lambda. And in order to apply this matrix on a vector, a typical vector, that would be v sub 1, v sub 2. This is a typical vector. And the answer should be 0, 0. Okay, so if lambda 1 is 1 plus 2I, the first matrix is going to be, let me find it here, 1 minus lambda is going to be 1 minus 1 plus 2I. It means 1 minus 1 negative 2I. So altogether, this one will be negative 2I. Same for this one. And these two remain the same. We have v sub 1, v sub 2 here. Now we're going to write the system of equation based on this equation. So in order to do that, we're going to multiply the first row and the column. So we would have negative 2I times v sub 1 minus 2v sub 2 equals 0, because this one here, the first one is 0. Now we're going to multiply the second row by the column that we have. So we would have 2 times v sub 1 minus 2I v sub 2 equals 0. Why do we do this? We do this in order to find the eigenvector. We are going to find how this matrix affects the given vector. Okay, so from this, you can pick the first one or the second one. If you pick the first one and you add 2v sub 2 to the both sides, you would get negative 2I v sub 1 equals 2v sub 2. And from here, we can cancel these two out, and negative I v sub 1 equals v sub 2. So this is the relationship that is between v sub 1 and v sub 2. You can pick any number, including a general number for one of them, and based on that, find the other one. So the things that I'm going to write here, all are correct. Let's say one of students say, I want to pick v sub 1 as number 1. with picking v sub 1 as number 1, let me give it easier. Okay, let me find v sub 2 as number 1. So in this case, if v sub 2 is 1, negative I times v sub 1 is going to be 1. So from here, v sub 1 is 1 over negative I. We know that in complex numbers, in order to get rid of this denominator, we would multiply this by the same thing, or at least with y. So y over y is good. The top will be I, the bottom will be negative I, because I squared is negative. So it will be only I. This is why in the solution of review, you see that a typical vector, let's say v, is 1 for v sub 2 and I for v sub 1. Okay. Same idea when lambda 2 is 1 minus 2i with the same process and a similar answer. But let's say somebody says, I don't want to do this. I want to pick v sub 1 as I. I is a number. This is correct to pick that at this. So if I is going to be v sub 1, according to the formula that we have here, the yellow one, v sub 2 is going to be negative I v sub 1. And this means negative I times I, which will be negative 1, which is 1. Okay, again, same answer. I 1 as the eigenvector related to the eigenvalue 1 plus 2i. Or maybe you say, I don't want to pick all these here. I want to pick v sub 1 as a general number, let's say alpha. This is fine also. If you pick v sub 1 as alpha, the relationship that we have here is important. If v sub 1 is alpha, v sub 2, according to the relationship that we have, is going to be negative I times alpha. And this is also correct. V will be the first component alpha, the second component negative I alpha. And this is also correct. So let's say another person wants to pick v sub 1 as 5. V sub 2 will be negative 5i, and v will be 5 and negative 5i. This is also correct. So overall, it all depends on the picking that you have here and also the relationship that we have. Also, I have seen another concern about this equation or this example, especially for the equilibrium value. So in order to do this, we pay attention to the definition. Definition is here, and equilibrium is a value of the vector for which no change occurs. So it means that v sub t plus 1 is going to be the same as v sub t. Okay, now, having this in mind, we're going to solve this equation. So you can treat this equation as, let's say, x equals 5x in algebra. So maybe you have the question that's why these two are the same, because of the definition of equilibrium. It says that if you're going to find equilibrium value, that would be a value that v of the next step is the same as the previous step, as we see here. So we can just name them as v or a or any other letter. They should be the same. This is why you see v and v here. So now, think of solving this equation in algebra. How can we solve this? If you want to solve this, one of the ways is subtracting 5x both sides. And we would get x minus 5x equals 0. Then we factor out x, 1 minus 5 here, and of course we know the answer. This process here can apply here as well. So if you want to factor out nu, you can, I'm sorry, if I say nu and v, consider them the same thing. This is nu, but I sometimes say we. So how can we do this? We're going to factor out nu here. So the left side is 1 and the right side is the matrix. We know that inside the parentheses is not correct in terms of mathematics. So instead of 1, we are going to write the identity. And since it is 1, the identity remains the same. If it was 5, we would write 5005 minus 100 negative 1. And inside the parentheses would be 0, 0, 0, and 2. And we know that a typical vector as v can be v sub 1, v sub 2 equals 0. Now you know how to do this. We're going to write the system of equation. That would be for the first part, if you multiply this and this, you get nothing. You get 0 equals 0. But for the second part, this and this, you get 0 times v sub 1 plus 2 times v sub 2 equals 0. From this, we would conclude that v sub 2 is 0. It cannot be any number. But in here, we don't have any conclusion about v sub 1. This is why we call it free. You can pick any number as we have talked before. So let's say somebody picks v sub 1 as number 1. So the vector v will be 1, 0 because v sub 2 is fixed here. But let's say v sub 2, somebody picks it as 5. So this will be 5, 0. Or as a general value, alpha, that would be alpha 0. And this is why the solution of the review, you see v hat can be k and 0. So that's a general number. But if you write 5, 0 instead of that, that is correct. This is 1, I'm sorry.